Hi, I'm going to talk about fall-offs, but first I'm going to do a detour, meaning I'm going to talk about normalization, which is a building block for fall-off. So we already talked about normalization for scalars, where I looked into the box step to basically fit some values between 0 and 1. And so by setting up the begin at -1 and the end at 3, I can guarantee that I have a black to white transition between those two values. I also looked into the remap node to perform that, and basically it's nice that it has the clamp option, so allows me to have some extrapolation or not. With the box step, there's never extrapolation because it clamps always. So it's nice, but it's also nice to have the option to not clamp. Now, for the vectors, normalization means something quite different. So basically, it means that if I have a position, let's say this position P, that has a certain length or a certain distance from it to the origin, if I pass that position through normalize, what I'm going to get is a version of that vector that has the same direction, but it has length 1. And so to normalize in vectors is basically to retrieve a unit vector. Now, I'm going to unpack this operation, this normalization operation in vectors. And the advantage of that is that when we unpack operations, we can replace components and get different outcomes. And so that's what I'm going to do. So this first level of unpacking, instead of just passing the vector through the normalize node, I'm going to pass it through the length node. And so the length node will give me this distance that goes from the origin to the position. To that amount, I'm going to basically invert it. So in this case, it's the multiplicative inversion, or 1 over L. And this factor here is going to be used to scale my vector. And so by scaling the vector by this value, I'm going to get the same exact thing as the normalized node. Now, a second level of unpacking would be to basically find the length by myself. So instead of using the node, I would have a node tree that explicitly expresses the calculation of the length. The length is found by the Pythagorean theorem. And so we have that the length squared is equal to the x squared plus y squared plus z squared. And so this is the expression that we get to find the length. So here I have these 3 power nodes that basically correspond to the powers that we see in the coordinates here. Then I also invert this power. So in here we have 2, and by doing its multiplicative inversion, we get 0.5. And when I use 0.5 here in a power node, I'm basically doing the square root. And so this is basically the same thing that we have here. Now, let's first look into this first level of unpacking and basically look like, instead of using the length, what if we use other things, other inferred data? And so here I have the first example, of course, that uses the length, and I have this mesh, it's this mesh right here. And what happens if I use the length in this operation in this mesh? Well, basically I get the unit sphere, just like I have here this unit sphere. I'm going to get the unit sphere out of the positions of this mesh. Now, if I use something else, let's say the sum of the channels, instead of doing the Pythagorean theorem on them, I'm just going to add them up together and use that in place of the length node. Well, if I do that, I'm not going to get a unit sphere. I'm going to get an octahedron. But there's some nice applications for this amount. So the sum here is basically the taxicab length. This is usually called the Euclidean length, is the distance that goes, let's say, I have A and B. And so this green line is the Euclidean length, but the sum is basically the path that I have to take to get from A to B. Let's say this is a city block, the layout of a city, and I cannot just go through the buildings of the city. If I pick up a cab, the cab will zigzag through the buildings to get from one position to the other. And of course, the distance that I cover in that path ends up being greater than the distance that goes in a straight line from one position to the other. So this is called the taxicab length because it's just the sum of the components. So if you look at that as our coordinate system, it's the sum of the component vectors that we had to add together to go from one position to the other. And so there are some nice applications for this type of normalization. So for example, I have these values here and they amount to 4. If I add them together, they amount to 4. So if I divide all of these by 4, instead of 0.4, I get 0.1. Instead of 2, I get 0.5. Instead of 1.6, I get 4. And what I can get with this is that I make sure that when I add them together, they amount to 1. And so that's useful, for example, for weight normalization. So here I have, let's say, this character with this bone, and I'm looking at the vertex 1 influences of the deformers. And usually we don't want the sum of the influences to go above 1, because that means that some deformer will be doing more than it should be doing. And so, for example, if there's for some reason some deformer that makes all of this go above 1, we can use the sum normalization so that we guarantee that when these are added together, they sum up to 1. Now let's look into another component. So instead of using the length, what if we use the maximum? So here I have this vector scalar node set to maximum. And so instead of using the length, I'm going to use the maximum. So what I get if I do that, it's not a unit sphere, but I get a cube. And so the positions will stick into the surface of a cube. And if I look into stacks like I did in here, what it's going to happen is it's going to pick the greatest value of all three. And it's going to use that as the scaling factor. So basically I'm going to divide everything here by 2 because this is the maximum value. And so 0.4 becomes 0.2, 2 becomes 1, 1.6 becomes 0.8. And so now all the values fit between 0 and 1. So these are some of the values that you can use instead of the length for normalization. Let's check that in layout. So I have this object here, and if I go into the Theorem tab, you can see that I have a morph that it's the one giving it's this displaced look. It's actually a sphere, and so I just have this morph, so I have some positions to work with. It's not actually a sphere that I can normalize. So I here in the displacement node editor, I have the world spot being distributed, and the first one I'm going to check is the normalized. And to check it, I have this subtract node here to perform the delta with the initial positions so that I can feed this into the displacement. And so by doing that, you can see that I get the unit sphere, so basically a sphere with 1 unit radius by using the normalized node. And I get the same thing if I divide the positions by their own length. So this performs the same thing as the normalized node. Now, by unpacking this operation, now I can replace the length by other things. So in this case, I here have the dot product performing the sum of the components of the first vector. And you'll notice that for the dot product and for the maximum, I have an absolute node before them. Why? Well, the length is always going to be positive. There's no negative length. It can either be 0 or positive. But for the dot product and the maximum, I can have negative values. So let's say that I have a vector like -2, -5, and -10. Well, if I pass this through the maximum, what I'm going to get is the -2. This is the value that is the greatest value of the. But what I want is not the greatest value, I want the longest value. So I also want a notion of length in this. And so the one that is most distant from the origin is actually 10. And so by doing the absolute, I get 2, 5, and 10. And now 10 is the maximum. And same will be true for the dot product. So when I talked about the taxicab length, it doesn't matter if the cab goes into a negative direction. What it matters is the covered distance by the cab. And so of course, I want to make those coordinates all positive. So I get the length of the covered distance that the cab did, not coordinates. I don't need to know if it goes into a negative direction. So let me replace the length by the sum, and by doing that, I get an octahedron. If I replace this with the maximum, you'll notice that I get a cube. Now, this can be quite fun. Let's say that I put the order of the displacement node editor to be before world displacement, so it takes into account the position of the object. And you notice now that it works like a constraint. So even if I rotate the object, it's constrained to that shape. It's normalizing to that shape, regardless. And I can even, for example, let's say here I make a swap. I put a swap vector node, and let's say that I want to check to see if this factor is greater than 1. And so if it is, basically I'm going to not normalize it. You can see that when it comes outside, it's not normalized. Or I can do the other way around. I can, for example, put this here, and now the normalization will act like a bounding box that when the mesh hits those walls, you can sort of see the container of it, right? And you can do that for the other one. So in this case here, it's one in here, and now the sphere becomes that bounding volume per se. If I scale this, Now let's look into this compound here. Basically what I have in this compound is these 3 options. And so I have position, basically the divide node with all of these 3 scalars. So length, and I have the position of it, the normalized position. So it's basically a normalized node here. I just decided this is something that I think I use at times, but all of these are mostly for the demo. And so here I have the length, the vector being divided by its length. I have the vector being divided by the sum of its coordinates, and I have it being divided by by the maximum. So I have the position and also the factor for all of them. I also have here the sign, as we've seen before, that gives me the octants, and I also have the longest axis, and I'm going to talk about this one next. But first, let's look into some instances. So I'm going to put this to the side. I'm going to change this back to local placement, and let's see. I'm going to move this to the side here. And I'm going to go into this instancer object. I'm going to activate its instance. And so what we see here now is a sphere, but this is actually a rectangle array. So if I go into the nodes, you'll see that if I disconnect this, I have this rectangular array. But by normalizing the base positions, and I also have to do a delta here because this is an offset, as you can see here. So if I normalize these positions, you'll see that I can also constrain them to one of these shapes and have the octahedron, can have the cube as well, right? And I can also do the check to see if the instances are inside or outside. So for example, I can do something similar that I did before, in which I can, let's say, for example, do this, and let's say that I use this one to check if it's greater than 1. See if the factor is greater than 1. Okay, I'm going to do the other way around. I'm going to choose this one. And now you'll notice that the ones that are inside are not being normalized. So they're still there. Let's do this with the length. Okay, so now you notice that when we see the inside, unlike before, where we had all of them being normalized, now only the ones that are outside that range, only the ones that are outside that range are being normalized. So this is always fun. It's the logic node works really well with these factors to check if something is inside or outside a certain range. Okay, so let's look into the other level of unpacking the operation. So here is the first level, and now the second level where I calculate the length by explicitly. And here I'm using the value of 2, the power of 2. And what if I use another power? What if instead of 2, I say I use 1? Or I use 0, or I use, let's say, 100. Let's check that. And so I'm going to hide these instances, and I'm going back to my sphere normalization object into the displacement, and I'm going to bring this here. Okay, so here I have the explicit Pythagorean theorem operation going on, and I have here the power defined, and the power at the moment is 2. So I have to also do an absolute here because I'm going to use other power values, and it might not give me always a positive value like the length node gives me. And so if I plug this in here, so basically what I'm doing is I'm finding the length and then I'm dividing the vector by that length. So it's basically the same thing as it's happening here, is that I'm expanding the length calculation. Whoops. So let's look into that. Okay, so I get the unit sphere, but what if I change the value of 2? Let's say I put 1 here. Oh, look, now I get the octahedron, just like the sum. What if I, say, put 0? Well, apparently it does nothing, but if I put, like, say, 5, oh, it gives me this strange shape. That it goes from that, if I start to raise it, to the octahedron, and from the octahedron, I go into the sphere, and from the sphere, if I keep raising this value, I eventually get to the cube. Let's say I'm going to put here 100, and, well, that's nice. So here I have these 3 calculated separately. Here is a way that by changing the power of the length, I can basically have a transition between them. And so to simplify this power calculation, I have this simple color corrector by DBNW tools, and I'm using the gamma, which basically uses the power function. Is the only difference is that it uses multiplicative inverse value as an input. So here I have the value that I'm using being inverted so that I can use this as a power function. And I also need to put the absolute because the simple color corrector, when it catches negative values, it basically outputs them as they were before. So I need to put positive values so that the power function really works. Now, what I have going on in here is basically the same thing as goes on in here. It's just instead of adding everything together with an add 4, I'm doing the sum with a dot product, and this power node corresponds to this power node, etc. So if I plug this in here, you can see that I get the same thing. So if I put, say, 50, put, let's say, 10, I get the same thing. That let me turn on Studio Live for a moment, and you can see as I slide the value, I have a transition between those shapes. Now, what's happening here is something that you can search on Wikipedia, where I took this image from. And so we have this transition by changing the exponent or power of the that's used in the length calculation, in the Pythagorean theorem calculation. And so when we use 2, we get our unit sphere, and so the radius then it's sort of the radius of the sphere. When we use 1, it's the sum of the coordinates. So in this case, I'm looking at this in 2D. So 0.5 plus 0.5 will give me 1. In this case, 1 is the radius. And then we have when the exponent goes into infinity, we get that's basically the distance to the axis. So it's just the size of the containing box. It's like a different type of radius in a way. And so here I have a compound that basically does what I've shown in here, and it's called normalize pow, because it uses the power function. And so if I plug this in here, you can see that I basically can do the same thing as that I was showing. The only difference with this compound though is that I have a second input called shape that allows me to basically go between shapes. So at 0, I get that shape that almost resembles nothing, and then as I start to go to 1, I get the octaedron, and then when I go to 2, I get the sphere, and when I get to 3, I get the cube. So it's much easier to make a transition between them, and you can also get access to the factor. So the thing that I've shown in here about checking if something is outside or not can be done by this factor here. So let's do that just to make the equivalent operations. Let's say this here. And so now, regardless of what's the shape that I have, it's going to act as a container. And so let's say I put here the shape of the sphere, right? This also acts as a container. Let's say I put the shape of the octaedron, and it also acts like a container. And let's say I put something almost going into nothing, and it also acts as a container. So this is just, to be honest, I don't use this much because these calculations are a bit heavy. Most of the times, this is just if you want to do a transition between them. Most of the times I use these simple calculations, and they work fine. I don't need to do a transition most of the times. I need them for specific reasons, like I've mentioned here, to normalize influences or to fit something. So it's not very common for me to use the one that allows me to do the transition. Now there are some applications for this, and I'm gonna talk about that when I get into the shading. So let's go into the surface editor. And let's see, I think for now, I'm going to leave the displacement for now. So let's go into the surface editor, and I have here basically the normalize and the normalize PAL compounds. And if I turn on VPR, we can see that if I put, let's say, the length into this gradient that has some colors that are to be cycled, if I put this here under the diffuse shading, you can see that I have a cycling gradient. So the length is being converted into colors. And so this is going to be a important part of our fall-offs. Basically, here is just for a visualization, so we can kind of see the distance colored, but you can sort of see, a spherical fall off, right? While if I, for example, let me take out Studio Live and let me put OpenGL overlay. So if let's say if I squash this a little bit, you can sort of see a spherical shape done by the length. The sum will produce an octaedron shape, and the max will produce a cubic shape. So this is our small library of shapes for that come from the sort of lengths that we infer, and so this produce this type of shapes. And like we've done with before with the logic node, we can use it to check if something is inside or outside a certain. If I put here greater than 1, I know that these points here are outside the radius 1. Or if I put, let's say, the sum, I know these points are outside the octaedron. I can even of course increase that range to 2 or 0.5, so I can, but it's a nice way to check if something is inside or outside. And well, basically here with the normalized POW, I can do the same thing with the factor. So I just need to decide what's the shape that I want. So if I put here 2, I get the sphere. If I put 1, I get the octaedron. 3, I get the cube. And that's it. Now let's talk about this axis 1. This axis output. So basically what this axis does, it's another compound that I have, but I decided to put everything in this one because sometimes these things are related. And so I just like to have a compound that has everything there for me. And so in this case, let's look into, instead of looking at the positions, let's look into the normals. And I'm going to reset the object, and I'm going to take out, for now, I'm going to take out the morph. All right, so if I have the normals in here and I put the axis, let's say this one first. Okay, so what is this giving me? This is giving me the longest coordinate. So let's say that I have a vector like this. right? And what I want out of this is I want a vector that gives me 0 for the coordinates that are not the maximum and gives me 1 for the coordinate that is the maximum. So for example, out of this, I would get the vector 0, 0, 1 because -10 is the longest channel. And so this gives me, basically it's a way that it allows me to filter so that I know what's the most dominant channel, right? And so in this case of the normals, you notice that these normals, when they face the x-axis, mostly they're going to become red. When they face the z-axis, mostly they become blue, and when they face the y-axis, mostly they become green. And so if, for example, if I put the morph back, you'll see that this still applies when the mesh is displaced. So why bother with this? Well, this ties a little bit with the simple color corrector being used as a way to do the power function. And let's look into that. So I'm going to use an absolute vector, absolute. And if I come here and I put this in color, right? Okay, so now let me copy one of these. Okay, now if I put this in here, you see that I get this soft looking directions. Of course, let's say if I normalize vector, normalize, if I do length normalization, no, actually, let me do the sum normalization. And so let me just first put something in here. So as I decrease the value here, you'll notice that these start to get darker and darker, but there are still values in there. I can't see them, but there's still something in there. And to bring those up, I'm going to use the sum normalization. And so basically what I'm going to perform here is what I've talked before in here about normalizing influences. So the values here are really small, but they are still there. So let's say that they are at 0.1, 0.3, and 0.01. These they don't give a sum that amounts to 1. So what I'm going to do is I'm going to normalize them by the sum so that their sum becomes 1. And so by doing that, what I get is this. Now, if I change this gamma value, you can see that basically what I'm doing is I'm softening the normals, right? And then you ask me, okay, that is fun, but what's the use of that? Well, this is something that's becoming very popular recently. That is to do a triplanar shader in which you have some projection images and you basically have them distributed on the mesh. And so you don't have much work basically distributing materials into different faces. You're not doing a cubic projection. And so by doing this, by softening the normals, what I can do, or actually in this case, I can make it really contrasted by putting 0.5, something like this. Now they look really contrasted, and this is what normally a cubic projection would do. Now I've done this compound here called X-planar shading, and basically what it does, it distributes 6 images. So here are the 6 textures. So it's 3 images and 3 procedural textures, and it distributes them on each direction. So on the X, in the positive X, there's a texture. On the positive, in the negative X, there's another texture, and etc. for all the other directions. Now I have this input here called softness, and if I put, let's say 0, I'm going to get no softening at all. And so these are very, very crude. But if I say put like 0.3, I start to get some blending between them. And so this the idea of these shaders, that you can texture things without much trouble and just use the normals to distribute the different textures depending on where the polygons are facing. And so that's the idea behind these type of shading. Normally you see a triplanar shading. In this case, I decided to call it X-planar because I use 6 textures instead of 3, but the principle is the same. If you want to have something to repeat, you just plug in the same thing into the both X inputs. So it's up to you. And then I also have here some influence for the positive and to the negative side that basically allows me to scale one of those sides. So for example, let's say I want the X axis to have less of an influence to the texture. You notice that this came down. So if I put 1 back, you can see that it goes back to normal. But if I put, let's say 0.2, you notice that it gets really small. So this allows me that the other textures blend in a little bit more. Okay, so this is basically a little demo of this X-planar shading. If we go inside, we basically see that we have the simple color corrector just used for the power function, and we have here the sum normalization where I divide the vector by the sum of its components. Okay, so now let's just finish this up by talking about another type of normalization, which is the volume normalization. And that can be seen, let me come here, that can be seen in the nodal motion. So I have here in the nodal motion, I have this little tree, and you can see this compound called the normalize vol. So what normalize vol uses to normalize, to divide the vector by, is the product of the components. So we've seen the sum that uses the sum of the components. In this case, it's going to be the product of the components. I'm going to multiply them all together. What this is going to give me is basically the volume of the sides that I'm defining. So for example, I'm starting with the base 1, 1, 1. So I'm going to have volume 1. And by normalizing the volume, I'm basically going to make sure that whenever I scale my object, it's going to maintain that volume of 1. And so if I come here and I connect this into the scale, as I change the y-axis handle, you notice that the other axes are also being scaled. So if I take this out, let me manipulate the y-axis, you see that only the y-axis is being changed. But by plugging this in here, you'll notice that now the other axes are being changed as well, and so the volume of this is maintained. So this sphere, or its container, is still has volume of 1, and I can do that for the three axes. So I can manipulate this one as well. Let's see, I've actually my mistake. I first used this one. Let's use first this one. Okay, so here I can do for any of the three axes, and so you can see here that it does the same thing regardless of the axis that I use. And then we have this other one, which basically I just input one value and I get the complementary values for the other axis. And so in this case, I'm just going to use the y-axis, and as I plug that in there, you can see that only the y-axis will perform that operation. And so yeah, basically here are just some fail safes, but the rest is just the basic operation that I've been talking about. I have an absolute, I have the product of the components, I have the power in this case to do the cubic root of the current volume, meaning the product of all components, so that then I get a factor by which I can scale them down to the volume of 1. So this is it. Next I'm going to talk more about point fall-offs and try to have objects control those. Cheers.